Alright, here we go with the last one before spring break. I won't be seeing you in South Padre Island, unfortunately, but hopefully you have a good time while you're gone. And I should have done a bonus quiz today because I'd have a lot less to grade, I suppose. But you guys are here, so thank you for being here. And speaking of bonus quizzes, the ones that we did on Monday, I'm still in the progress of entering. So if your last name starts with M or before, I've gotten you in. But I got interrupted by a fire alarm, so I couldn't finish them today. But I'll get them done either later today or early tomorrow. And if your score is missing and you think you were here for the quiz, just let me know and I'll get that sorted out. All right, so today we're going to keep going through things related to aqueous solutions. This is more Chapter 6 material, some pretty foundational stuff here that's going to be important. This week's homework is still only on Chapter 5, so we're a little bit ahead now finally, but this stuff is still important and somewhat related to a lot of things we've already talked about. So the first thing we're going to talk about, last time we finished with, and I'm sorry that the one video didn't work, but I think I got it to work on Chrome browser, so if you have the link from the last lecture and you want to watch that video, hopefully you can get it to work like I did. But we talked about the idea that when an ionic compound dissolves in water, what happens is that the polar water molecules surround the ions, they bring them into solution, they surround them completely, and they completely separate the ions from one another. So in the solid ionic compound, the positive and negative ions are attracted to each other and held together in a tight solid, and then in solution, the water molecules rip those apart and completely separate them. So then that relates to some very simple concepts of sort of dealing with stoichiometry of what happens when we dissolve ionic compounds in water. So this question is a pretty typical one we like to ask and is important to understand, which is if we take 3 grams of silver nitrate and we dissolve it in water, how many moles of ions are present in that solution? Okay, so we have a mass amount. We know how to convert masses into moles, but there's one additional thing we have to keep in mind here. So we're going to take our silver 1 nitrate, which is AgNO3. And so when we dissolve a compound in water, when we dissolve an ionic compound specifically, what happens is we add that to water. Sometimes you'll just see people put water above the arrow or to indicate that you're dissolving it, not that water is actually participating in any sort of chemical reaction. And then what you get are the 2 ions that make up the ionic compound. So AgNO3 is Ag plus and it's NO3 minus, and those 2 separate. And for anything that's happening in water, whether it be a physical process like this, just dissolving a compound, or when we start talking about chemical reactions of dissolved ionic compounds, if it's dissolved in water, we put a little AQ next to it to indicate that it's an aqueous species. Okay? So we separate the 2 ions, we dissolve them in water, and so the key point here is that if we're starting with 1 mole of compound, AgNO3, we end up getting 2 moles of ions, okay? Because the ions separate out. And if it had been a more complex ionic compound, you could get more than 2 moles of ions. But this one has 1 Ag plus, 1 NO3 minus. So when it dissolves in water and separates, you get 2 moles of ions out of this. And that's going to be the important concept then for solving the numerical question that we're asking. So we want to find the moles of ions in this situation. And we're told that we are starting with 3 grams of silver nitrate. And we know from many examples last time and the time before that how to convert grams into moles. So we use the molar mass of silver nitrate, which is given to us as 169.87. We divide by that number because we're going from grams to moles. So we have 169.87 grams of AgNO3 in 1 mole. But remember, that gives us the moles of silver nitrate, the intact ionic compound. And what we're interested in here is moles of ions. Okay? So we have to do the one last step, which is recognizing that when this ionic compound dissolves, we're going to get 2 moles of ions for every 1 mole of AgNO3 that we dissolve. Alright? So it's kind of like, in some sense, an analogy to the bonus quiz we had last time. If you want to find the number of atoms in a sample, you often have to multiply by how many of that atom there are. In this case, if you want to find out how many ions are in a sample, you have to account for how many ions are composing that compound. In this case, there's 2 of them. And so what we get then, if we multiply this out, is 0.3 0.0353 moles, which people that would try this on their own, most likely the second most common answer would be half of this, forgetting to do this last step here of multiplying by 2. And then we can do that, this is for total moles of ions, we can do that for individual ions as well. So this one's a pretty simple one. For 1 mole of AgNO3, we're going to get 1 mole of Ag plus, or 1 mole of NO3 minus. Again, if the formula is more complicated, if you had 2 of one ion or 3 of one ion, then you'd have different ratios and different relationships there. But we can use simple ratios like this to determine the total number of moles of ions or the moles of an individual ion when we dissolve it. So that's kind of a quantitative picture of what happens when we dissolve ionic compounds. We had talked about the qualitative picture last time. And this introduces then a new relationship involving moles called molarity. So in chapter 5 we talked about 2 relationships involving moles, the molar mass, which relates mass to moles, and then Avogadro's number, which relates number of entities or number of particles to moles. And in this chapter we introduce a third one, which is molarity. And so the idea with molarity is if we want to quantify how much of a compound is dissolved in a solution, we need some sort of a unit to define concentration. There are actually a few concentration units, and you'll learn more of them in chemistry too, but the one that we'll focus exclusively on in this course is molarity. And so we need a precise definition for molarity. So this is, as I said, a concentration unit. So it's a way of quantifying how concentrated a solution is, in other words, how much stuff it has dissolved in it. And it's going to be a ratio of 2 quantities. So we're going to take moles of solute. So remember that we said solute is whatever is dissolved in the solution, typically the minor component. And then we're going to divide that by liters of solution. So it has a very precise definition. So the numerator has to be in moles, which is a typical unit, but then the denominator of this, the volume part, has to be in liters, not in any other volume unit. And the other thing that we should keep in mind is the precise wording of this. This is liters of solution, not liters of solvent. Okay? Now, in reality, when you prepare a solution of an ionic compound, as long as the concentration is not ridiculous, the volume of the solution you get is going to be almost exactly the same as the volume of solvent that you're using to dissolve that compound. If you do this in the lab, you'll see that. But in reality, the precise definition of molarity, you need to know the actual volume of the solution that is formed when you mix the solute and the solvent together. So, the volumes are not necessarily additive, or sometimes the volume expands or contracts depending on the properties of the solution you're making. So the volume of the solution is not necessarily given by just the volume of the solvent or even by the volume of the two added together. So you need to know the volume of solution to be able to calculate this precisely. The abbreviation for this is just capital M. Okay, so that's the abbreviation. And so, for example, if we took 2 moles of solute and divided it, or dissolved it in 1 liter of solution, so this is the volume of the solution, the denominator, we would call that a 2.0 molar capital M solution. Okay, so always keep in mind that this capital M represents a ratio of moles per liter. So this is another one of those what we call intensive properties of a solution in this case, where it doesn't matter how much of the solution you have. If you make a 2 molar solution, if you take 1 drop of that solution, the concentration of that 1 drop is still 2 molar. If you have a whole liter or bathtub of that solution, the concentration will still be 2 molar. So it's a ratio of 2 quantities, so it doesn't depend on how much solution you have. It's the ratio of those 2 things. Okay, but it is a relationship that involves moles. It's a ratio, so we should start thinking about how we can potentially use this as a conversion factor, as we'll see in a little bit here. But first, let's just talk about how to calculate molarity in just a slightly more complicated sense. So if we have sulfuric acid, if you take concentrated sulfuric acid, pure sulfuric acid, and you add it to paper or cotton or anything with hydrocarbons in it, it turns black and disgusting. So don't put it on your skin is I guess the short story there. But anyway, if you take sulfuric acid and we take 15 grams of it and we dissolve it in enough water to form 200 milliliters of solution, we're asking here what is the molarity. So we're asking you to calculate the concentration in molarity units with this bit of information. So whenever we're trying to calculate molarity, we know that the two pieces of information we need are moles of solute and liters of solution. Okay, so moles of solute is pretty straightforward for us at this point. We have 15 grams of H2SO4. We have the molar mass, where we could calculate if we didn't have it. So converting grams to moles should be old hat for us now. So H2SO4 is the solute, it's what we're dissolving into the solution. So we calculate the moles using its mass as the starting point. So we divide by the molar mass to get grams into moles, same calculation we've done a million times. Alright, so this solution has 0.153 moles of H2SO4. Alright, and then what we're going to do is we need to find the liters of solution, which is the other part of this. So we can put that up here, 0.153 moles. And then for liters, and this is where you have to, again, be careful with units. So in the laboratory setting, milliliters is the much more common unit, although molarity is defined per liter. So we need to always convert our volumes into liters if we're going to be using that. So we haven't seen volume units too much in this course yet, but our milliliters is 10 to the minus third. So if we want to go from milliliters to liters, if we have 200 milliliters, we're going to use a ratio of 1 liter per 1,000 milliliters. A milliliter is 1,000 times smaller than a liter, so you do it like this. Or you could do 10 to the minus third liters per milliliter, whatever you prefer. But anyway, we convert that into liters by dividing by 1,000, and that comes out to 0.2. And we put this back up into our denominator to get the molarity. So moles per liter is molarity, and I forgot to calculate this. I think it's 0.465. So the question is, can I do math in my head, because I forgot to calculate this before. Oh, jeez. 765. I'm losing it. Okay, 765 molar. So you just divide the two, provided you have an appropriate calculator and appropriate level of intelligence to do that, unlike me, and you get 0.765. Okay, so it's just a simple division problem once you have the two quantities that you need. But like I said, especially for the denominator, be careful with units. It has to be liters, and it has to be liters of solution if you're given other types of information in the problem. Let's do a slightly more complicated one, where now we're going to use molarity as a conversion factor. So let's say we have a solution of hemoglobin, which is the protein found in red blood cells. And we want to know how many of these hemoglobin or heme molecules is a short way of saying that. I guess heme is the little cofactor that goes into hemoglobin technically, but there's, anyway, how many heme molecules are there in 25 milliliters of a 0.00150 molar heme solution? So we're using, in this case, molarity as a conversion factor. So we want to know how many molecules there are. So just with any problem, let's write down what we're looking for, and then figure out how we convert into that. Okay, so we have two choices here. We have volume of our solution, and we have molarity. What are we going to use as our starting point? Typically, we want to use the volume as our starting point and not the molarity. The molarity, as I said, we're going to use this as a conversion factor. So let's not put that at the beginning of the problem. Let's start with the volume of solution we have, which is 25.0 milliliters. And if we're looking for number of molecules, we know that there's a relationship between moles and number of molecules, which is Avogadro's number. So the first thing we should try to do is figure out how many moles we have, and then we can convert that in the final step. So trying to think about it a little bit backwards where we're going to. So the first thing we should do is, we have milliliters of solution, we have a molarity. Remember, molarity is moles per liter. So if we can convert this into liters, we will be able to then calculate moles of solute. So we're going to do this. This first step is going to convert milliliters into liters. So again, 1 liter is 1,000 milliliters, same conversion factor we used in the last one. All right, now we have liters of solution. We can use the molarity as a conversion factor to figure out how many moles of heme we have. Okay? So the molarity is 0.00150, and that's moles of heme for every 1 liter of solution. All right, so that's going to give us the moles of heme that we have, but we're looking for the number of heme molecules, individual molecules. So the last step, which is also familiar to us, we're just combining molarity with some other things we already know, is to take Avogadro's number, 6.022 times 10 to the 23rd heme molecules per 1 mole of heme. Okay, so that's the definition of a mole. And we use that to calculate the number of individual molecules, and we end up with a number that's 2.26 times 10 to the, I believe that's a 19, can't read my own writing sometimes, molecules. Okay? So again, this is combining this idea of molarity with something we already know. One thing I'll start to do in some of these problems, probably not until after today, but as a little bit of a shortcut you can keep in mind, is that we don't, if we have milliliters of solution, we could kind of combine these two conversion factors here and say that another way of thinking about molarity is that it's moles per 1,000 milliliters. So that's a shortcut I'll start to use later on, but it would save us a step if we use it. But you can do it in multiple steps, however you're comfortable with it. But the key being we have to get moles first using the molarity, and then we can convert into other things like mass or number of molecules as we did here. Alright, so that's just an example of how we use molarity. Now the next thing I want to talk about is what's called dilution, which is the idea of changing the molarity of a solution by adding more solvent to it. Okay? So the way that the picture for this works is, let's say we have a concentrated solution. So what I'm going to do is I'm going to represent the water with blue, and then I'm going to draw little red solute molecules. So let's say we have 10 solute molecules dissolved in here. So what dilution, the picture here, what we're doing is we're taking a concentrated solution, with some molarity associated with it, and we're going to put that into pure solvent, or vice versa. We're going to add pure solvent to the solution. So one way to think about dilution is we take this solution, which has all of our solute molecules dissolved, and we pour it into pure water, and that's going to change the concentration. Now what we should realize is that when we pour this top solution into the larger volume in the bottom, the number of solute molecules doesn't change. The 10 solute molecules that we have dissolved up here are all going to go down into this larger volume here. We're not losing solute, we're not gaining any solute. So it's still the same number of solute molecules, or same moles of solute, but now they're just more spread out in a larger volume. Alright, so still 10 solute molecules as I've drawn it, but now in a much larger volume. So up here we have a solution that has a larger molarity, more moles per liter, and a smaller volume. And then down here we end up with a solution that has a smaller molarity. Solute molecules are more dilute, more spread out, and it has a larger volume. Okay, so we're not changing the number of solute molecules. So let's get some definitions and some other things down on paper here. So the definition of dilution is we're adding pure solvent to a solution, or vice versa. So we're not mixing two solutions together. The precise definition of dilution is that we're adding pure solvent to a solution, or the opposite as I've drawn it here. And by doing that, we make a solution with lower concentration. Okay? And the key point, which I've tried to illustrate in this picture here, is that the moles of solute stays the same before and after the dilution. So we're not losing or gaining solute molecules. We have the same number at the beginning, just in a smaller volume, and we still have the same number of solute molecules here in the larger volume after the dilution. Alright, so you probably are at least somewhat familiar with the concept of dilution in your everyday lives. Trying to think of one that doesn't involve alcoholic beverages, but the idea of changing the concentration of a solution by adding more solvent to it is really what we're getting at here. Or some people say that dilution is the solution to pollution, which is not a particularly good saying if you care about the environment, but that's also out there. Okay, so that's the definition of dilution. Now what we want to talk about next is the dilution equation. So what are we going to be doing with this numerically, and how do we determine how much the concentration changes when we do a dilution? So this can be easily derived from the definition for molarity. So as we just talked about a little bit earlier, molarity is moles of solute divided by volume of solution, or specifically the liters of solution, as we talked about, but we'll just call it volume here to make it more general. So if we just rearrange this equation, we just cross multiply, putting the volume on the other side, we get that molarity times volume is equal to moles of solute. And as we talked about, in a dilution situation where you're just adding pure solvent to change the concentration, the moles of solute stays the same before and after the dilution, so we're going to use that to then get the relationship between those starting and initial conditions. So the moles of solute that we initially have is equal to the moles of solute that we end up with in our final diluted solution. And so we're going to take this product of molarity and volume for the initial solution we have, and then set that equal to the product of molarity and volume for the final solution, because the moles stay the same. And so the familiar dilution equation becomes M1V1 equals M2V2. Okay? This product M1V1 is the moles of solute we have at the beginning. That's equal to the moles of solute we have after the dilution, but it's just different molarities and volumes that give that same product. So this is the dilution equation here. And so that's what we're going to use whenever we're doing a dilution problem. So part of the trick is recognizing when to use this equation. And as I said, you're only going to really want to use this when you're adding a solvent to a solution to make a different concentration. You don't want to use it when we start talking about chemical reactions that happen in solution, or we can't use it if we're just talking about a single solution that we're not diluting like we did earlier. But if you're talking about two solutions that you're changing the concentration of, you're going to want to always think about this equation and how to use it. Alright, so let's just do a couple of example problems. So let's say we have a sodium hydroxide solution that's 6.00 molar, and we want to end up preparing a 250 milliliter solution that's 0.5 molar. So how much of this concentrated solution are we adding to make 250 milliliters of the 0.5 molar solution? So we should recognize this is dilution because we have the same substance before and after. It's just sodium hydroxide. We're not changing it to something else by doing a chemical reaction. We have a molarity that we're given. We have a final volume and molarity at the end. And we can just then use the dilution equation to figure out what volume of this solution are we going to put in there to make that. So we're using M1V1 equals M2V2. And typically in these problems, because it's only a single equation that we have, you have one unknown and 3 of those 4 variables are going to be given to you. So we're looking for, and what you call M1 and V1 and what you call M2 and V2 is arbitrary. You just have to make sure the right ones are matched up with each other. So if our final volume is 250 milliliters, we'll call that V2. If our final molarity is 0.5 molar, we'll call that M2. You could have also called those V1 and M1 as long as they're matched with each other. And then the initial molarity is given to us as 6 molar, that's our M1. And so what we're solving for here is V1, the amount of that 6 molar solution we're going to use during this dilution. Okay, so we just rearrange this equation and solve for V1. So M2 times V2 divided by M1, and that'll give us the volume of that first solution we need to put in here as part of this dilution. So we just start plugging numbers in. Now, one thing you might be curious about is, well, do we have to convert V2 into liters? You can, but you don't have to, because in this case it's a ratio. So we have, if we put the units in, our M2 is 0.500 molar, V1 is 250 milliliters, and then we have 6.00 molar is M1. So we're plugging these numbers up that we got in the problem up into here. Molarity cancels out, and that would give us then an answer in milliliters. Now, I didn't specify what unit we wanted for this problem, so if you would have solved it in liters, that would have been equally acceptable, but we don't need to go through those conversions, because in this equation we only have one volume unit. The molarities cancel out, so the molarities don't so the volumes don't necessarily have to be in liters. And similarly, if we're solving for molarity, as I think we'll do, no, so we won't do that, but if we're solving for molarity instead, if we have milliliters on the top and bottom, those will cancel out. So as long as you keep track of the units, as long as you keep track of which ones cancel out, for these types of problems, they don't necessarily have to be the standard units of liters in particular. So that's a long way of saying the units don't matter as much for this one, as long as we keep track of them, and when we multiply and divide, we get 20.8 milliliters. So what this means is that we would take 20.8 milliliters of our 6 molar solution and then dilute it to a volume of 250 milliliters, and when we do that, the new concentration is 0.5 molar. So presumably you'll do this in chemistry lab if you haven't already, or certainly by next semester you will talk about how to dilute solutions, how to make them, and this is the kind of calculation you would do. And as long as the units are consistent, they can be milliliters or liters or really any other volume unit that you want, provided that the concentrations are in molarity as they are here. Take questions on that one? Alright, so the next one is just a little bit more complicated. Same type of problem, but what we have here is concentrated phosphoric acid in this case, which is 90% by mass. So concentrated phosphoric acid has that concentration, but it's a mass percent that we're giving you here, and the density is 1.5 grams per milliliter. And we want to know how many milliliters of this solution are needed to prepare 2 liters of a 0.1 molar solution. Now we should recognize this as a dilution problem, because we're adding a concentrated solution, and we're changing the concentration, making it more dilute. So we can use the molarity equation. We have a couple of those things given to us already. So this is going to be our V2. This is going to be our M2. So same story as before. We're solving for V1 really, but we don't have the initial molarity. So M1 V1 equals M2 V2. We're looking for the volume of that concentrated solution that we're going to use to prepare the less concentrated solution. So it's same rearrangement as before. We have M2 and V2 given to us directly, 2 liters and 0.1 molar. However, in this case, M1 is not directly given to us. So the concentration unit that we use, did I mess this up? No, this should be M1, sorry. Alright, so this is the rearranged equation solving for V1. This one, we need this number to be able to solve it, but we don't have it directly here because the initial concentration we're given is in mass percent. Now this is another concentration unit, not the most common one, but what this means, and we kind of already know what mass percent means, is that this solution has 90 grams of solute, H3PO4, per 100 grams of solution. So mass percent for a solution means the same thing as it does for a compound. 90 mass percent means you have 90 grams of solute per 100 grams of solution. So that's what that 90 mass percent means. But we have to go through a little bit of effort here to find out what this initial molarity is, because mass percent and molarity are not equivalent to each other. They're two separate concentration units. So we want to find the initial molarity, M1. Keep in mind that this is going to be moles per liter. So that's the units that we want to end up with. And we're starting with a concentration that's 90 grams of H3PO4 per 100 grams of solution. That's our initial concentration unit that we're given. And so we have to figure out a series of steps that are to convert this into molarity, moles per liter. So if we look at the numerator first, we want the numerator to be in moles. The numerator is in grams. Do we know how to convert grams to mole? I sure hope so by now, because I've done it a million times. So we do that by using the molar mass, which I gave you at the end of the problem, 97.99. So 1 mole of H3PO4 has a mass of 97.99 grams. So grams cancel out. Okay, so that's going to be moles in the numerator, which is what we want. So we're taken care of there. But now we have to figure out how to change 100 grams of solution, which is our denominator at the beginning, into liters of solution, which is what we need to be able to determine molarity. So to do this one, we can think about this relationship here of density. So we haven't used density a lot, but it's one of those topics that was assumed that you would have already known from previous chemistry or other science courses. So we're going to use density to convert grams of solution into a volume. So 1.5 grams per milliliter, we want grams to cancel, so if we multiply by that density, 1.50 grams in 1 milliliter, so 1.5 grams of solution is a volume of 1 milliliter. So grams of solution cancels out. So now we have moles per milliliter. We're getting close to moles per liter, and the last step is then to convert milliliters into liters. And again, knowing whether we multiply or divide by the density, whether we multiply or divide by the conversion factor from milliliters to liters, comes from just carefully writing out the units and keeping track of them. So we want grams to cancel, so grams of solution has to be in the numerator here, so the density is written as this. But then if we want to go milliliters of solution in the denominator into liters, we multiply by 1,000 milliliters per 1 liter. Milliliters divide out, and that gives us now liters of solution in the denominator, moles of solute in the numerator, and we've converted the units correctly in this case. So a lot of steps to do this, but it allows us to calculate the molarity, which ends up being 13.8. So that's our M1. That's not what the question is asking for, though. We need that to solve it. What we're looking for, again, is the volume of that solution that we're going to use to prepare 2 liters of the 0.1 molar solution. So now that we have M1, we can just plug that into the dilution equation. So V1 is equal to M2 V2 over M1, as we saw, and we just put the numbers in. So M2 is the final molarity, which is 0.100. V2 is the final volume of that solution, which is 2 liters. And then the initial molarity that we just calculated is 13.8. So again, molarity cancels out, and this gives us, in this case, liters, because that's the unit we have up here. But then if you look carefully at the question, we're looking for how many milliliters of this solution are needed. So we have to multiply that by 1,000 to get milliliters. So especially for, well, really any time, whether it's multiple choice or free response, make sure you look carefully at what units we specify for the whatever you're solving for. And especially for things like volume, sometimes it'll be milliliters, sometimes it'll be liters. You have to keep them straight. So this volume in milliliters is 14.5. So if we want to make a 2-liter solution that's 0.1 molar, we just take 14.5 milliliters of our concentrated acid, add that to enough water to make 2 liters of solution. Alright, so same story as the last one, just introducing a little bit of a trick here of being able to convert different concentration units into molarity. Like I said, the vast majority of things you'll do will be with molarity, but occasionally we'll give you another concentration unit like mass percent, and you'll have to convert them as part of these problems. Alright, does that any more questions on molarity and dilution before we move on? Alright, so what we're going to get into next are describing some of the chemical reactions that occur in aqueous solution. So the rest of this chapter is about classifying those types of reactions that occur in aqueous solution, and then some of the stoichiometry aspects of those that we'll sort of end with, because that's all kind of related. So the first one we'll cover is called a precipitation reaction. So let's define what that is. So in a precipitation reaction, we're combining 2 aqueous solutions. So initially all of the and what I should mention is that these involve ionic compounds. So We're mixing 2 aqueous solution of ionic compounds together. So initially all of the compounds are dissolved into the solution. You have homogeneous, clear solutions. And then one, or sometimes in rare cases more than one, insoluble products forms. So that insoluble product or products are called the precipitates. That's why we call it precipitation reactions. And there's another little saying in chemistry: you're either part of the solution or you're part of the precipitate. So anyway, I think I'm going to botch that, but there's a play on words there that I just messed up. But the precipitate is the insoluble product that forms when you mix these 2 ionic compounds together. Now, you can't just mix any 2 random ionic compounds together. You won't always get precipitation, but you do sometimes, and we'll learn how to predict when you do and do not get precipitation. That's kind of our goal for today, for this part of it. So that's what happens when we mix 2 solutions together. If you remember, if you were here on I think maybe the very first day of class, I showed a YouTube video of that demonstrated law of conservation of mass, and that was a precipitation reaction. You mix 2 solutions together and you get this solid that forms that's no longer dissolved in the solution. So that's what we mean by precipitation. Now, the steps to determine whether or not a precipitate will form, that's kind of usually goal number 1 in these types of problems. We have to separate the reactants into their ions. So as we talked about at the very beginning today, when you dissolve ionic compounds in water, they separate into the individual ions that make them up. So we separate the reactants into their constituent ions. In the video that I showed on the very first day of class, which if you go back to the lecture notes, you can watch it again if you want, it was this reaction here, I believe, or something similar to this. So we took potassium iodide as aqueous solution and mixed it with lead nitrate, lead 2 nitrate specifically, so PbNO3 lead 2 plus with 2 nitrates. And so if we want to separate these 2 reactants into the ions that make them up, the potassium iodide is just K plus, and it's going to be now dissolved in aqueous solution in I minus. And then when we dissolve lead nitrate in aqueous solutions, we get lead 2 plus as the cation. And then we release 2 NO3 minuses. When we have a subscript of 2, we're going to generate 2 of those anions when we dissolve it. So we get 2 NO3 minuses. So we have to consider the individual ions that are present in these ionic compounds, which is usually obvious from the formula, but you need to make sure you keep track of all of them. And as well as stoichiometry can be important too, the coefficient of 2 in some cases. Now we consider all possible combinations of these ions with each other. So usually there's going to be 2 products that are possible, and the way that we form these 2 products is we take the cation from one reactant and we pair it with the anion from the other, and vice versa. So if we take the cation from our first reactant, which is K+, that came from potassium iodide, and then we combine that with NO3-, that's going to be one of our products, this cation with the other anion, so it's KNO3. And then the other product, we're going to take lead 2+, which is the cation from our second reactant, and combine it with I-, which is the anion from our first reactant. So we're just swapping cations and anions with each other. They're just trading them with each other, if you want to think about it that way. And so if we take lead 2+ and I-, the correct formula for that would be PbI2, because it's a 2+ cation, so we need 2 I- to pair with that. So we're thinking about which ionic compounds can form when we swap cations and anions with each other. And then the last step is to decide whether either of these products, either of these combinations of ions that we get, forms an insoluble ionic compound. And this is what we're going to learn how to predict right now, so we need to know what are called solubility rules. Now, a lot of students hate solubility rules. I'm just warning you, but I don't want that to be the case for you guys. So a lot of people look at this, and especially if you look at it in your book, the way they present it in the book, it's just a list of rules. You know, these compounds are soluble, these compounds are insoluble. You know, rule 1, rule 2, rule 3, rule 4. And it gets kind of overwhelming to look at it and think, oh, I have to just memorize these. But what I like to do is introduce this in a slightly more systematic fashion. There are things you're going to have to just remember and get familiar with, and the more you practice it, the more familiar you'll become. But I like to separate these different cations and anions in different categories, and you want to always look for the obvious ones first when you're doing problems like this. So some cations and anions are obviously going to always be soluble, always going to be insoluble. You find those first when you're trying to identify what the precipitate is, if any. So let's go through the solubility rules using sort of the way that I think about it, which is dividing up different cations and anions into categories. So what I'll call category A are ones that are always soluble. And so what this means is that if one of these cations or one of these anions appears in the compound that you're considering, that compound will be soluble. You don't have to think about what the other ion is. You don't have to think about anything else. If you see one of these ions in the compound, you know that the compound is soluble. So soluble, now when we say a compound is soluble versus insoluble, it's kind of an arbitrary definition. I think the dividing line is if you can dissolve, I think it's a pretty low amount, if you can dissolve more than 1 milligram per liter, which is a very small amount, you would classify that as soluble. And if you can dissolve less than 1 milligram per liter, you classify those as insoluble. And again, another teaser for chemistry too, when you take that course, you'll learn more of the quantitative aspects of how we define solubility. But for now, we're just going to divide everything into two, black and white categories, soluble and insoluble. And so if you see in one of these ions in the compound that I'm going to put in category A here, the compound will always be soluble. And most of these are pretty easy to identify. So the majority of the cations that you're considering here are going to be those group 1A alkali metal cations. So there's only one that's not outside of this. So if you have an ionic compound that has lithium plus, sodium plus, K plus, rubidium plus, cesium plus, all of those cations that come from the first column of the periodic table, any ionic compound that has those in it is going to be soluble, and that's end of story. Now there's one more outside of these that we have to keep in mind. This polyatomic cation, one of the only polyatomic cations we have, which is ammonium NH4+. So NH4+ gets grouped in with these as well. So any ionic compound that has these cations in it will be soluble. And then there's some anions that fall into that category too, meaning if the compound has this anion, regardless of what the cation is, the compound will be soluble. And these ones are a little bit harder to remember because they're all polyatomic. So nitrate NO3-, perchlorate ClO4-, and then acetate, which can be written in two ways. The way that I like to write it is CH3COO-, the negative charge is on this last oxygen here, or sometimes you'll see it written as C2H3O2, which doesn't give you as much information about the structure of that ion, but it's still the same formula. So two ways of writing the same thing, which we call acetate. So these three anions, nitrate, perchlorate, acetate, are always found in soluble ionic compounds. So if you can remember these ones, look for those first, because if one of the products has one of those anions or cations in it, it will be soluble and it won't be forming as a precipitate in that reaction. Okay? And then we have another category, which are cations and anions that always form insoluble compounds unless they're paired with one of the ones above. So these rules are also kind of a hierarchy in some sense. So if it has a cation or anion from category A, it will be soluble, no exceptions. And then for category B, if it has one of these cations or anions, it will be insoluble unless it's paired with a cation or anion from group A. All right, so the cations that fall in this category are silver plus, and this is the classic one that you'll see in a lot of these problems as forming a precipitate, and the one we just looked at in that example I started with, lead 2+. So lead 2+ compounds are always insoluble unless they're paired with nitrate, perchlorate, and acetate. So lead acetate, lead perchlorate, lead nitrate, all of those would be soluble, but any other ionic compound with lead 2+ in it would be insoluble, and same with silver. The anions that fall into this category would be carbonate, CO3 2-, phosphate, PO4 3-, sulfide, S2-, and chromate, CrO4-. Sorry, 2-. Okay? So those four anions, unless they're paired with lithium, sodium, potassium, rubidium, cesium, or ammonium, one of those special cations that I gave you in the first category, all those anions will be insoluble ionic compounds in whatever compound they're in. So unless it's one of those group 1A or ammonium. Yeah?
Does the other like lead, when that 2 charges plus 2 something else, that also part of one that
So you're talking about like lead 4 plus? I don't think we're going to consider lead 4 plus for solubility rules. It would be different though. So it does, if you have, and I think we'll get to some examples with transition metals a little bit later. So if you have a cation that can form more than one charge, which is true for lead and is true for most of the transition metals, the different charges will have different solubility rules. We're not going to have you learn and remember all of those differences. So I think most lead 4 compounds are also insoluble, but it's probably a little bit different than lead 2 plus. But I don't think we'll see any examples with that anyway. But it's a good question. Anything else? I think there's another hand up. Yeah. It just means and. So there you go. All right. So that just means that those two are the examples of cations that are almost always insoluble, except when they're with one of these anions. Okay. So that's the Sorry.
Sorry. For category A, so Fr plus is also soluble, right?
Well, Fr plus is radioactive, so we don't typically do precipitation reactions with it. But I think it would be yes. Yeah, so if it's also in that column, you would assume it's soluble, but that's not a very common one. All right, but all good questions. And then moving on to the next one, so there's only 2 more categories to go to. So we have category C, which is usually soluble unless paired with category B. So remember, category B are the ones that tend to be insoluble, and then there's some cations and anions that they're going to be soluble unless they're with one of those. So again, let's try to remember this as a hierarchy. So halides are usually soluble. So that's specifically Cl minus, Br minus, and I minus. F minus is a little bit different, as we'll get to, but I don't think we're going to worry about that one. So those halides are usually soluble unless they're with silver or lead. So silver chloride is insoluble, lead chloride is insoluble. But if you have a different cation with those, sodium, calcium, or most of the transition metals, you would assume that those are soluble if they have halide anions. And then there are a couple other exceptions, though, to this. So most halides are soluble except for silver, lead, and then Cu plus, which is isoelectronic with silver plus, so not surprisingly it behaves the same way. And then this polyatomic mercury cation, Hg2 2 plus, mercury 1 but 2 mercury 1 bonded to each other, also give insoluble halides. So there's more than just those exceptions, but if you see halides, Cl minus, Br minus, I minus, you can pretty safely assume they're soluble unless it's silver, lead, copper, mercury. So those 4 are sort of the exceptions to the halides being soluble. And then finally, the last category are kind of the in-between and annoying ones where they have as many rules as exceptions, so you have to just kind of brute force learn these ones. So one of those is going to be SO4 2 minus sulfates. These are usually soluble, but there's more exceptions than we have for the halides, which is why I put it down in this category here. So they're soluble except with category B, which is lead and silver, the ones that are pretty much always insoluble. But there's also other exceptions for sulfates. So the heavier alkaline earth ones, so calcium, strontium, and barium, those sulfates are insoluble, so you have to remember those. Calcium, strontium, and barium sulfate are also insoluble sulfates. So sulfate has more exceptions, but more often than not it is soluble. And then another one that's sort of the opposite of that is OH minus. This one is usually insoluble, so hydroxide compounds are usually insoluble. Of course, the exceptions to that would be category A, those cations that are always soluble. Lithium, sodium, and all the way down to francium if we want to go down that far. But then this has, OH minus has the same exceptions as SO4 2 minus, but it's the opposite exception. So calcium 2 plus hydroxide, barium hydroxide, and strontium hydroxide are soluble and not insoluble. Right, so they're kind of similar in some sense, but they have obviously the opposite exceptions. SO4 2- is usually soluble except with calcium, strontium, barium. OH- is usually insoluble except with calcium, strontium, barium. So they're kind of the same exceptions, but they work in opposite directions. So that's kind of how I like to think about the solubility rules, and learning them in this sort of hierarchical fashion I think will be very helpful to many of you and get you through a lot of these problems easier. Here's the full list of rules reproduced for you. This is from your book, so if you don't have the book, you can see it here. And again, there's a few more things in here than what I gave, but I think I tried to organize them in a little bit more logical fashion. So you just have to learn those. But let's go through then how to write the chemical equations then for precipitation reactions, aqueous ionic reactions. So there are 3 ways that we can write these types of chemical equations out, and we're going to learn how to do all 3 of them. One is called the molecular equation. This is probably the most common way to write it, especially for precipitation reactions. So molecular equation is what I gave you earlier. It's the full set of reactants and products, and we don't separate the ions in this case. So we write all the reactants and products as intact species. We don't separate them for the molecular equation or the formula equation. A couple ways of saying that, but it's the full, it's the full equation with the identities of all the reactants and products. So for the one we've been talking about, potassium iodide plus lead nitrate, we would just write it like this: Ki. Anything that's dissolved in solution, we put an AQ next to. So potassium iodide is soluble. The reactants are always going to be soluble in these types of equations. And you have lead nitrate, which is also soluble. And then, as we said, the 2 possible products are KNO3. We swap the cations and the anions with each other. KNO3 is soluble. Potassium is always soluble. Nitrate is always soluble, so no question about this one. And the other product is PbI2. And as we said, lead compounds are almost always insoluble unless they're with one of the special anions. So because this compound is a precipitate, because it's insoluble, we don't put an AQ next to it, we put an S next to it to indicate that it formed as a solid. It's no longer dissolved in solution, so the aqueous notator is no longer appropriate. And then we should go through and balance this quickly. So on the reaction side, we have 2 NO3 minuses. We need to put a 2 there. Now we have 2 potassium, so we put a 2 there, and that also balances iodine. So you will have sometimes coefficients for these. They tend to be small. I can't think of a precipitation reaction that has a coefficient larger than 3. So it's usually going to be like 1s, 2s, and 3s, some combination of those. Pretty small coefficients, but make sure that everything's balanced. And it's sometimes helpful to think of intact ions together instead of trying to balance, for example, nitrogen and oxygen separately. They're always together as nitrate. So just look at how many nitrates you have on each side. That can help you with coefficients and stuff like that. So we balanced it. Now the next type of chemical equation we can write is what's called the total ionic equation. So in this case, we're going to separate anything that's a soluble ionic compound into its ions. So anything that has an AQ next to it, we separate into ions, as we've already talked about happens. And this becomes a little bit long, and because we have to separate all of these soluble compounds into reactants. So if we have 2 Ki's that we separate into ions, we would get 2 K plus and 2 I minuses. Each Ki has 1 of each, then we have 2, so 2 K plus, 2 I minuses. This one's soluble, so we get a Pb2 plus, and then 2 NO3 minuses. So those are all of the reactants separated into ions. Reactants, as I said, are always soluble, so they will separate. And then on the product side, we form KNO3, which is still a dissolved aqueous compound, so that's going to give us 2 K pluses on the product side as well. 2 NO3 minuses from that KNO3. But then we have to be careful. We don't want to just go, crazy and separate everything. We have PbI2, but that's a solid, that's insoluble, so we don't separate that into ions. So we write that still as PbI2 solid. So only things that are soluble compounds will actually separate in solution, and so we finish it with that. So that's the total ionic equation. That has all of the ions present, all of the compounds separated into their ions. And then finally, net ionic equation, we have to remove what are called spectator ions. And these are the ions which appear on both sides of the equation. And they appear on both sides as dissolved aqueous ions. Alright, so if we look at this equation we wrote above, we have K plus on the reactant side and we have two K pluses on the product side. So K plus is one of our spectator ions. I'll put an X under it to indicate that. So that's one of the spectator ions. Then we also see that NO3 minus, we have two NO3 minuses as a reactant, two NO3 minuses as a product, both dissolved aqueous ions. So those are also spectators. And so when we remove those, we get what's called the net ionic equation, which just has the two ions that combine to form the precipitate. So you'd get Pb2 plus is still left. Conventionally, we write cations first and then anions, but you don't necessarily have to do that. Two I minuses, and then those combine to form Pbi2 solid. So this is what's called the net ionic equation. It just includes the ions that are changing from aqueous to a precipitate, from the reactants to the product side, and that leaves out K plus and NO3 minus, which are the spectator ions. And as we talked about, K plus and NO3 minus are two of the ions that are always soluble, no matter what they're paired with, so those will typically always be spectator ions because they're never going to be involved in forming a precipitate or doing anything else. Okay, so that's how we write different types of equations. Let's do an example of one just to wrap this up. So we want to write the molecular total ionic and net ionic equations for the reaction that occurs between sodium sulfate and silver 1 nitrate. So we have three equations to write. So part of this is going to be making sure we know our nomenclature well that we learned in chapter 3. Because we're not giving you formulas for compounds. We have to write them out from the names. So we have sodium sulfate and silver 1 nitrate. So sodium sulfate is Na2SO4 because SO4 is 2 minus, so sodium is 1 plus. Okay, because sodium is in the first column of the periodic table, so it forms plus 1 cations. So that's going to be one reactant, and all sodium salts are soluble. And then the other one is silver nitrate. So similar to before, we have a nitrate compound. Silver 1, silver plus 1, NO3 minus, so it's just AgNO3. Nitrates are always soluble, and for these types of problems, reactants will always be soluble too. And then what we're going to form as products, remember, we're going to swap the cations and the anions with each other. So the first compound has sodium cations, and we're going to pair that with the anion from the second one, which is NO3 minus. So we're going to pair Na plus NO3 minus to give NaNO3, sodium nitrate. And from solubility rules, we know that this is soluble because sodium and nitrate are always soluble. So that's kind of our no-brainer. And then the other product, we're going to take silver, we're going to pair it with SO4, 2 minus. So if it's silver plus 1, we don't change the charge of the cations ever. We're not doing that yet. That's later in this chapter. So for precipitation reaction, we don't change any charges. So this is silver 1, still going to be silver 1 in the product. And so if you have silver 1 and we pair it with SO4, 2 minus, we also need to have Ag2SO4. That's going to be the correct formula for silver 1 sulfate. And then we have to decide if this is soluble or insoluble. As we said, silver compounds are always insoluble unless they're paired with nitrate perchlorate acetate. So this is not one of those soluble exceptions. So we're going to write this as our precipitate with an S next to it. And we need to put some coefficients into balance. So we have 2 silvers on the product side, so we put a 2 there. And then we have to put a 2 there to balance the sodium and the nitrate. And I think everything else is all set for us. Okay, so small coefficients are going to be required, but typically not too difficult to balance these. So that's our molecular equation. And then just like before, our total ionic equation, we're going to separate these out into ions. So sodium sulfate separates into 2 sodium pluses, because it's Na2SO4, 1 SO4 2 minus. These are all dissolved ions on the reactant side. Silver separates into Ag plus and NO3 minuses, and there's 2 of them. So we get 2 Ag plus aqueous plus 2 NO3 minuses. And then finally on the product side we have our sodium nitrate is still dissolved. There's going to be 2 Na pluses and 2 NO3 minuses. Those are both aqueous. But then our second product, Ag2SO4, is insoluble, so we don't want to separate it into anything. And that still has a little S next to it that I keep running out of room to write. So that's going to be the total ionic equation. Everything that's a dissolved, soluble ionic compound we separate into the individual ions. And then finally, for net ionic, we find the spectator ions. So Na plus appears on both sides, and so does NO3 minus. So similar spectator ions as the last one. And so the only things that are involved are silver and sulfate, and we write this out in a balanced form with 2 Ag pluses plus SO4 2 minus going to Ag2SO4 as a solid. Alright, so a lot of similarities to the last one, but just another way to practice that from start to beginning. So learn how to do these. We don't often ask about total ionic equations, but sometimes we do. But the most common ones are molecular and net ionics. You have to be able to progress through and get those different forms of these ionic equations. Alright, questions on that before we move on to today's last topic. So the last topic we're going to start talking about today is acid-base chemistry, which has a lot of similarities with what we just talked about, but we're using different kinds of compounds here, as the name implies, acids and bases. So let's first define what those are. We kind of know from a nomenclature standpoint what an acid is, but now let's talk about more of its chemical definition. So there's a lot of different definitions for acid. We're going to focus on what I think is the simplest one in this course. It's a compound that releases H plus when it's dissolved in water. So we know from the nomenclature section when we learn how to name acids that acids all include H plus, one or more H plus ions as part of the formula. And when you dissolve them into water, they're going to release some or all of that H plus into solution. So they release H plus when dissolved in water. And as we already talked about, the formula for acids are pretty easy to recognize. They start with hydrogen, they have some number of hydrogens, and they're paired with an anion, where X can be either a simple or polyatomic anion, and the number of hydrogens that's paired with is dictated by the anion's charge. So each charge that you have on the anion is compensated by 1 H plus. So N is the charge of whatever the anion is. So we learned how to name these a while ago, so we should be able to recognize them. And now we know from a chemistry standpoint, when we dissolve them in water, they release that H plus into solution. That's what characterizes them as acids. Okay? So not every compound that has hydrogen in it will be an acid, but some of those H pluses are able to be released into solution when we dissolve them, and we'll learn which ones those are. Now, a base we haven't seen yet, and a base is a compound that releases OH minus in water, hydroxide. So most bases have the formula, they're just a salt of a hydroxide. So you know, a compound that releases hydroxide in water, not surprisingly, is a hydroxide salt. So that's what most bases look like. There's some sort of hydroxide compound, where again N is dictated by the charge. Of whatever cation is paired with that hydroxide anion. So those are what bases are. They release OH minus, acids release H plus. Now within acids and bases, we sort of talked about this a little bit when we were discussing electrolytes at the very beginning of this chapter last time. We have what are called strong and we have weak acids and bases. Okay, so we have to be able to recognize which ones are strong and which ones are weak. That's going to be important for their chemistry that we'll talk about. So strong acids and bases are acids and bases that dissociate completely into ions. So that means when you dissolve them into a solution, the ions that make up those acids and bases, either the H plus for the acid with the anion or the OH minus for the base with this cation, those ions completely separate, and you have all those ions being released into solution. And as we talked about earlier, these give what are called strong electrolyte solutions. So when you dissolve a strong acid or a strong base in water, because you have all these ions around, they conduct electricity really well, and they're classified as strong electrolytes. Okay? So they're a lot like ionic compounds in that respect. Now, most bases are ionic compounds, as we talked about, and then acids behave the same way. Strong acids, when you dissolve them in water, they separate into the two ions, H plus and whatever anion they have. Now, we need to recognize which acids are strong and which ones are not. I think I gave this list earlier, but I'll give it here again. So the halogen acids, the hydrohalic acids, HCl, HBr, and HI are all strong. So those are all in that. Those are all those group 7 halide anions. Those acids are all strong, excepting HF is a weak acid. And then the other strong acids we should recognize are nitric, perchloric, and these two are pretty easy to remember because, and this isn't the reason why they're strong, but these are the two always soluble anions, or 2 of the 3 always soluble anions. So 2 of those give strong acids when they're paired with hydrogen. And then the last strong acid is sulfuric, H2SO4. Alright, so you'll need to remember these 6 strong acids and be able to recognize them. There are others, but we won't worry about them in this course. And then strong bases, the only strong bases we have are the soluble hydroxide compounds. So as we just discussed a little bit ago, most hydroxide compounds are insoluble. The ones that are soluble are the ones that we classify as strong bases, because when we dissolve them in solution, that hydroxide anion gets released into solution, and that's what we defined as being a base. Okay, so the ones that are strong bases are just the soluble ones. That's going to be all of our group 1 hydroxides: lithium, sodium, potassium, rubidium, and cesium being the ones that are conventionally used. And then finally we would have the other soluble hydroxides that we talked about are the heavier group 2 hydroxides. So calcium, strontium, and barium. Okay, so bases are easy to recognize because they have OH in the formula. The caveat being, if it's going to be a strong base, it has to be soluble. So you have to remember which ones are soluble and keep that straight in some cases. In most cases, that doesn't matter. If we give you a hydroxide compound, it's going to be one that we're expecting you to know behaves as a strong base. But it has to be soluble for that to work. And then finally, we have weak acids and weak bases. And these are ones that do not completely dissociate. We're not going to talk about the extent to which they do dissociate in this course. That's a Chemistry 2 topic. But they're ones that do not completely separate into ions when you put them in solution. So they do still release some ions. So when you dissolve a weak acid in water, you're going to get some H+, but just not a lot. And what ends up happening is that most of the molecules that you dissolve of that weak acid or weak base are intact, and they don't separate at all. And for a typical weak acid, it's a very small percentage of molecules that actually dissociate. But some do, and that's why we classify them as acids. And so the weak acids that you should recognize that are most common, I mean, pretty much any acid that's not listed above is weak. You know, it's not listed with these strong acids up here. But the ones that are most common are HF, H3PO4, and then acetic acid, CH3COOH. So acetate with an extra hydrogen on it. So those 3 acids are the most common weak acids that you'll see. And then finally, the only weak base we need to worry about, and it's not obvious why it's weak base, so I'll show you here, is ammonia, NH3. So that's the only weak base that we're going to discuss in this course, and it's a very common one. And so why is this a weak base? It doesn't have hydroxide in it, so how does that work? Well, what happens when you dissolve ammonia in water, NH3, it reacts with the water to produce hydroxide. So NH3, to some extent, reacts with water to make NH4 plus and OH minus. Alright, and it's this OH minus that then classifies this as a base. So as we said, this is a weak base, so you're not going to get much of these products, but you're going to get a little bit of hydroxide in solution, so we still classify this as a base, but it's a weak one. And that's the only weak base that we'll see here. So that's how we recognize strong acids and strong bases, weak acids and weak bases. Let's talk about then what happens when they react with each other. So what's really happening when we have a strong acid and a strong base combining with each other specifically, we're going to have H plus and OH minus recombining with each other to make water. So in every strong acid, strong base reaction, regardless of what the identity of the acids are, and provided that the other product is soluble, which it usually is, for strong acids and strong bases, I think that would always be the case. So the net ionic equation for any strong acid, strong base reaction is just the H plus from the acid reacting with the OH minus from the base to make water, which is a liquid. So H plus plus OH minus to make H2O liquid. That's the net ionic equation for any strong acid, strong base reaction. It's just a recombination of those two to make water. But the full equation is going to have some spectator ions and possibly some coefficients in it, which depend on what the actual identities of the acid and base are. Oops, I didn't spell that right. Alright, so they're pretty much all going to have the same net ionic equation, especially if it's a strong acid with a strong base, is what I wrote, but the exact equation and the identity of the spectator ions can vary a little bit depending on what the acid and the base are. So then when we have the full equation, if we want to write that out and consider all the spectator ions, the overall outcome of an acid-base reaction is always the same. You take an acid and a base and you react them with each other, and you're going to get two products. You're going to get water as one of your products, and then an ionic compound as a second product. So the ionic compound that forms in these acid-base reactions comes from whatever counter ions are associated with the acid and the base. So this ionic compound that you form is going to have a cation that came from the base. So as you said, most bases are hydroxide salts with some cation that's balancing the charge, and so the cation in the product that forms is going to come from that base, and then the anion is going to come from whatever acid you used. Alright, so another way you'll hear people say this is acid plus base gives you salt plus water. Alright, but it's not just salt as in sodium chloride, it's really any ionic compound that you can have from an acid and a base. So that's what the overall outcome is going to be, so let's look at some specific examples of that. So a simple one to start with is a 1-to-1 reaction with nitric acid and potassium hydroxide. So these are going to be a strong acid and a strong base, so the simplest type of acid-base reaction. And so we take the acid, which is nitric acid, HNO3, and we combine that with our base, KOH, soluble ionic compound, so it's a strong base. And as I said, the two products you're always going to get are going to be water. So the H plus and the OH minus combine to make water. And then the other product is going to be the ionic compound that forms from whatever ions are left behind. So from the base we have K plus, that's our cation. From the acid we have NO3 minus, which is our anion. Those two are going to combine with each other to make the other product, which is KNO3. You do need to think about the solubility of this compound that forms, because sometimes acid-base reactions include precipitation as well, but this one is clearly a soluble aqueous species, so you'd write it like that. So again, acid plus base gives you water plus ionic compound. The ionic compound comes from the base, the cation from the base, and the anion from the acid. Now, an easy way to balance acid-base reactions, just like precipitation reactions, the coefficients tend to be small. usually not bigger than 2s and 3s. Sometimes you'll have a little bit bigger than that. But the easy way to balance it is look at how many H pluses does my acid have. Has 1. And each H plus has to react with 1 OH minus. The base also has 1 OH minus. So if they each have 1 of each, they react in a 1-to-1 ratio. So the H plus and the OH minus that come from the acid and the base always have to combine in a 1-to-1 ratio to make water. So that can sometimes help you balancing these. But they're also not too difficult to balance just using the regular approach we use for balancing chemical equations. Now the second one that I'm going to show you is also strong acid plus strong base, but this time we're going to have some coefficients involved. So if we have sulfuric acid, H2SO4, and again the same base, KOH, potassium hydroxide, we're still going to make two products. We're going to make water as our, always going to be a product in the acid-base reaction, and then the ionic compound, we have potassium paired with sulfate. Potassium is 1 plus, sulfate is 2 minus, and so it's going to be K2SO4. That's the soluble compound, so it's still aqueous. Alright, so we wrote the formulas out. Again, an easy way to help us balance these is, if we look at our acid here, H2SO4, we have 2 H pluses. So if we have 2 H pluses in our acid, that needs to have 2 OH minuses to react with it. The base KOH only has 1 OH minus, so we need a full 2 of those to be able to balance that. And then if we have 2 of those, I think we need 2 in front of water. So if you have 2 H pluses and 2 OH minuses, you get 2 molecules of water. Now it's important to be able to balance these completely. As we'll see in reality later on, when we're doing acid-base stoichiometry problems, which is going to be something we'll get to a little bit later, the most important thing is to have the ratio of the acid and base correct, which is 1-to-2 in this case. You can balance the products after the fact and make sure that if you need the balance reaction that those are included, but getting the ratio of acid and base comes from how many H pluses and OH minuses you have. Now let's talk a little bit about acid-base reactions that involve weak acids. So if we have a weak acid involved, let's do one for acetic acid and barium hydroxide. We get acetic acid is CH3COOH. Barium hydroxide is BaOH2, soluble ionic base. And then we're going to form again still water. And the ionic compound that we form is barium 2 plus with acetate, CH3COO minus. There needs to be 2 of those to balance the charge. So it looks the same at this point. Acid plus base, water ionic compound. We need to balance it. CH3COOH only has 1 acidic proton, it's the one that's on oxygen. That one's acidic, so it's 1 acidic proton, 2 OH minuses, so we're going to need to have 2 of those to balance, and then 2 waters are formed as a result. Alright, so again, 2 H pluses, 2 OH minuses, very similar to the one we showed you before, except this time it's 2 acids and 1 base reacting. So the total equation looks very similar, but if we want to write out net ionic and total ionic equations, we have to keep in mind that acetic acid is a weak acid. And so when we're writing out ionic equations, we don't want to separate acetic acid into ions. Only strong acids do that. Weak acids largely remain intact. So when we're writing out ionic equations for weak acids, we don't separate the CH3COOH. So it's still dissolved, it's still aqueous, but it's not individual ions when it's a weak acid. So keep that distinction in mind. We don't separate this out because it's a weak acid. We leave it intact. The barium hydroxide is a soluble ionic compound, so when we separate that, we get barium 2 plus and 2 OH minuses. And then on the product side, we still have to separate ionic compounds. So water is clearly not an ionic compound, so we write that as so. And then we're going to get barium acetate, which is also soluble because all acetate compounds are soluble. So we get barium 2 plus and CH3COO minus. And there's going to be 2 of those because of the little subscript 2 there. So that's the total ionic equation, but we don't want to separate out acetic acid into ions because it's a weak acid. And then for the net ionic equation, what we notice is that there's only one spectator ion in this case. The only ion that appears on both sides is barium 2+, so we can remove that as a spectator if we want to write a net ionic equation, which would have 2CH3 COO minus, or COOH's acetic acid, 2 OH minuses, and then on the product side we get 2H2O plus 2CH3 COO minus. So that's our net ionic equation, which we have coefficients of 2 all the way across, so we can reduce this. So sometimes when you write net ionic equations, you get coefficients that can be reduced down to something smaller. So we have 2, 2, 2, 2 on everything, so we could just write our net ionic equation more simply as CH3COOH AQ, acetic acid plus 1 OH minus gives 1 water and 1 acetate. Alright, so that's how we do the net ionic equations for weak acids. You have to remember not to separate the weak acid into ions. So since we're out of time, I'll push off the last two until next week, and we'll start talking about some other types of aqueous reactions as well. But I guess